All right, as promised, we're going to talk about projectile motion and then finish up this module on kinematics. Um, so, as you are well aware, a tossed rock or tennis ball, or really any object that's projected by some means and continues in motion by its own inertia is called a projectile. And its inertia basically is a Newtonian idea of essentially an object's willingness or ability to move. Something that's hard to move has a lot of inertia because when you push it, it takes a lot of push to get it to move, and then when it starts moving, it also takes a lot to stop it. So small objects have small inertia, large objects have a lot of inertia. So let's talk about this whole idea of a projectile. So in a situation where we have a projectile, the object's velocity has a horizontal and a vertical component. Okay, and you can see that over here in this drawing of this girl throwing this ball. So you can see this main vector is pointing where she's throwing it. So the length identifies the speed by how much how hard she's throwing it. And then the direction shows where the ball's going. So this is a vector quantity. And the whole idea is that if we were to draw a coordinate system here, so if we were to draw a coordinate system and have an x direction and a y direction, the whole idea of this horizontal and vertical component is essentially in the x direction, this ball, if we just look at how this thing is moving from side to side, we don't care if it's going up or down, we sort of just track what it's doing from left to right. Well, this is our x component of the velocity. And the same thing, if we ignore what it's doing side to side and just watch it go up and down, sort of like we were riding along the side of it, well, that would be its y component of its velocity. And now both of these things together make up its main velocity, the direction of travel here in blue. So the horizontal component, so this orange piece here, I'm going to switch to black for now. So the horizontal component is completely independent of the vertical component of the velocity. That is when you ignore air resistance. Okay, so what goes on in x does not affect what goes on in y. What goes on in y does not affect what goes on in x. Okay, so x and y function independently. So it's important to note that the horizontal velocity, so the x, the orange direction, is not affected by gravity. Okay, so it's going to stay the same. Gravity is not eating away at its velocity. Gravity is not adding to its velocity. It's just going to move from one side to the other, same speed, if you ignore air resistance. Okay. So the idea here is we look at the x stuff going on and the y stuff going on. We can look at those things separately, but then when we put them together, that's how we get this a projectile motion. Okay, so when we look at these two independent pieces together, that makes up the object's trajectory. Okay, so gravity, it's still a free fall problem, so to speak. The only thing acting on this object is gravity. So gravity is the only acceleration pulling the ball downward. But again, the horizontal isn't affected by gravity. So let's actually take a look at the spacing here. So if we think about just the x piece, just like in the previous one, the orange here, if we think about the x piece, you'll notice There's no acceleration. These distances, all these distances are the same, which means it's traveling at the same speed. And if you're traveling at the same speed, that means you're not accelerating. No acceleration. That's only the motion in the x direction. If we look at the motion in the y direction, which I think I used red on the last slide, if we look at the motion in the y direction, you'll notice they're close together, they're a little further apart, they're a lot further apart. Here, the ball's already on the ground. So remember, our distance here, ooh, no, that's not an equals. No. This is a, oh, I did it again. Why is my eraser not working? Hold on a second. Strange, my eraser's not working. But anyways, this is proportional to t squared. So you can see that the distance is increasing. It's not the same chunk. Each piece is larger than the last. So we know that there is an acceleration because gravity's downward. So there is acceleration. That bugs me. I don't know why my eraser's not working. So if we take both of these pieces together, the horizontal constant speed and the acceleration downward, here's what we get. We get this motion. So you can see the distances are the same horizontally, but the vertical distances are increasing just like you would expect. Okay, so we have to superimpose both of these types of motion. You can see that here. All three of these are together. And that's essentially what projectile motion is just thinking about what's going on left to right in the x direction and what's going on up and down in the y direction. Just like a Cartesian grid that you've done lots of graphing on, I'm sure. Okay, now notice that the horizontal component everywhere along the trajectory is the same. So instead of just shooting something off a table, we're going to start from the ground, do a full arc, and land on the ground again. But in the x direction, which I've been using orange, so in the x direction, look at what's going on here with the horizontal component. In all of these time steps, the x direction is the same length. We're ignoring air resistance. It's negligible. There's no gravity in the x direction. There is no reason for the x component to change length, to change speed. To a longer vector would mean it's faster. A shorter vector would mean it's slower. There's no reason for that to happen here. Look at what happens here at the peak, though. This is interesting. So here at the peak, since this is where the velocity, the up-down velocity, remember in the last lecture we said at the height, the maximum height, the vertical velocity is 0. That means our main vector, our light blue vector, it has to be equal to the horizontal component because the horizontal component is the only velocity this thing has right now at this particular point in the arc. So that's why you only see the one vector. The horizontal piece and the main blue vector here, they're the same thing for this one instance in time. Now, if we look at the horizontal component, well, we know this thing's traveling in an arc, so we know it has to have a vertical piece But because of gravity, gravity is going to eat away at our vertical piece over time. So we're going to have minus g, which is going to make it shorter. We're going to have another minus g because gravity each time step is eating away. There is no vertical velocity here. It's neither positive nor negative. It's zero. But then by the time we get on over here, and the rest of the arc here, gravity's already made it change directions and it's pointing down, and instead of getting shorter, it's getting longer because this object is speeding up as it heads toward the ground. Okay, you'll notice that the red arrows are the same length, or the red vectors are the same length, just opposite directions. Same speed, opposite velocities. Same thing here. Same speed, opposite velocities. Okay, and like I've already said, at the top of the trajectory, the vertical component's zero. So let's talk about this launch angle. So we'll switch to blue. So our main vector just shows literally where the direction of this ball, this object is headed. Okay, but it's made up of these red and orange, or these red and orange components, the X and Y components. Look at what happens if we increase our launch angle. So now we have this crazy big launch angle. Okay, so the whole idea here is we're making our launch angle more vertical. So that means our vertical velocity is going to be even bigger. It's going to be even larger. Okay, even though it's larger and we launch, it still is going to be eaten away by gravity over time. So we still have minus some gravity, minus some gravity. When we get up here, again, it's neither positive nor negative, it's zero at the highest point. That's not true for the horizontal velocity. We'll get to that in a second. But just like you would expect, as it goes down the other side of the arc, the speeds are the same, but the velocities are opposite. So you can see the arrows are actually getting longer because over here, since it's actually heading toward the Earth, gravity is going to start assisting it for each time step. Now again, remember, there's nothing in the X direction, no air resistance, nothing like that. But look at what happened here. Because of our launch angle being so crazy high, you can see that because it's so high, we just really didn't get a lot in the X direction. When we cranked that angle up, we dumped more and more of that combined velocity into the vertical component. And if we put more into the vertical component, we have to take some out of the X component. So that's why in the X direction, our orange vectors are really tiny. But you'll notice that they stay the same length the whole time. That's because there's no accelerations in the X direction to change it. So it's going to stay constant the whole time. So something cool about projectile motion when you're doing these 2D problems, there's actually two different angles that can get to certain positions. So the whole idea is essentially almost any range can be obtained from two different angles. So if the two different angles add up to be 90 degrees, it's going to land you in the same spot. So you can see that here 15 degrees, a 15-degree launch angle will land you here. At the same time, you could also use a 75-degree launch angle, which will also land you at the exact same spot. And of course, 75 degrees plus 15 degrees equals 90. So the whole idea here is you can go really fast in the x direction, so 15 degrees, but then be so close to the ground that you just hit the ground really quickly. That's what's happening at 15 degrees. Or you can go so high in the air that you have so much hang time that you can actually make it over to the same position. And then we can even label, let's see, I'll do this. So I'll highlight these. So we can even do the same thing with 60 degrees and 30 degrees. Same position, 2 different angles. And then of course 45 plus 45 is 90, but that's the same angle. So there's only one 45 example. So we can even confirm 60 degrees plus 30 degrees. It's also 90 degrees. So as long as they add up to 90 degrees, you can get the same thing. Same distance, I should say. So that being said, let's actually think about what happens if we do include air resistance. So when air resistance is small enough to be ignored, projectile will rise to its maximum height in the same time it takes for it to fall that height to its initial level. So essentially, the ideal path, the time it takes, so the time it takes to get up there is the same as the time it takes to get back down to the ground again. Okay, we know that, we've sort of shown that. That's just because the deceleration and the acceleration is the same value. It's either plus or minus 10 meters per second squared on either side. But if air resistance is significant, basically that's when your horizontal piece is going to start slowing down, because once you have air resistance, the air resistance starts eating away at your horizontal velocity. So with air resistance, you'll actually start seeing your horizontal vectors get smaller and smaller until they're quite tiny. So just a quick aside here. This Russian high school math teacher, who's also a rocketeer, he made great contributions to rocketry in the early 1900s. His name is Konstantin Tchaikovsky, and he actually came up with essentially a rocket equation. So this is Tchaikovsky's rocket equation down here in the bottom right. And I just wanted to include this because he's sort of the father of rocketry. He helped get people into space. He also come up with a way to include the craziness of a rocket that has a changing mass and the fact that they are continuously propelled. So he was able to incorporate that into this equation, which was sort of one of the foundation equations for rocketry. So the whole idea is that you have a rocket plus fuel, but as the fuel burns, that rocket becomes lighter and lighter. So its dynamics change as you burn the fuel, and you have to account for that. Like, that's way beyond this course, but I still wanted to present you with an example of sort of how you know the basics and the basis of these projectile problems. But now that you've got the basics, you can start thinking about these things like, oh, what if the mass changes? Well, what if something is sort of changing in real time? Plus, this class is energy, tech, and society. So we got to include some, tech and society in here. So the neat thing here with his equation, and you all should be able to see this, is that instead of the old classic, which you all have used, the classic final velocity equals initial velocity plus AT. You've used that, we've talked about it. So here, he's got his final velocity equals the initial velocity plus, now here's his acceleration term. So really that's the same thing as AT, except instead of just doing a constant acceleration, He's included the velocity of the exhaust coming out of the back of the rocket. He's also included the initial mass of the rocket and how that mass changes. So we're going to do a delta n. So it turns out in rocketry, mass will also affect the velocity, and the velocity of the exhaust will. So this is much more complicated than just a simple constant acceleration problem. But there's enough pieces here where you can look at this and understand the rocket equation. You can sort of know what's going on here. So that's all I had for projectile motion. I just wanted to show you these problems, and at least give you something to think about in terms of next time you're playing basketball or baseball or something. You can actually think about your x components of the ball and the y components of the ball. So that's going to finish up everything in the kinematics module. As always, if you have any questions, please let me know. And after this, we'll move to Newton's laws of motion.